Hello and welcome to today's webinar session. Today's webinar is titled Creating High-Performance Real-Time Applications for NXP i.MX RT. My name is Mark Clark and I am the moderator for today's session. I'd now like to introduce you to today's presenters. We firstly have Anders Rosvall, who is the Technical Director at Embedded Artists. And we also have Vladimir Marchenko, Product Manager from MDK at Arm. Right, on today's agenda, firstly we will start with Anders Rosvall from Embedded Artists, who will discuss i.MX RT1052 OEM board overview. Following after Anders, we will have Vladimir Marchenko from Arm, who will discuss application development and debug, with a short introduction and then a demo of MDK and ULINKplus and i.MX RT1052 Developer Kit. At the end of the webinar, there will be a slot for questions and answers. I would urge everyone who has any questions to place these in the live chat window, and then the relevant person will be able to try and answer as many of those questions in the time that we have remaining. A recorded version of this webinar will also be made available to all those who have attended, and then you may be able to watch this at your leisure and also share with any of your colleagues. I will now hand over to Anders, who will begin presenting from Embedded Artists on the hardware aspects and show you how this will work with you today. Thank you.
Thank you. For those of you unfamiliar with Embedded Artists, let me give a quick introduction. We provide ARM-based computer module solutions built on NXP technology. We have families of pin-compatible boards. The one we will look at today is our OEM board family that is designed for microcontrollers. We have an industrial focus and we offer at least 10 years longevity. We are a proven partner to NXP, meaning that we have a lot of knowledge of our products and have a proven track record of our products. We provide high quality technical support directly from our engineers, and our slogan is the art of embedded systems made easy, meaning that we want to lower the thresholds when working with embedded systems. It's easy to get started when working with our products. Let's have a closer look at the i.MX RT1052 OEM board that is used in this webinar. It's based on NXP's i.MX RT1052, a 600 MHz Cortex-M7 with 0.5 MB of on-chip SRAM. That is a lot of performance, especially for being a microcontroller class product. Besides the i.MX RT1052 itself, our OEM board has 4 MB of octal SPI flash, 32 MB SD-RAM, 100 megabits per second Ethernet PHY and an optional Wi-Fi module. All this is packed in a small SODIMM 200 form factor. The i.MX RT1052 doesn't have any on-chip flash, so the application must be stored in an external flash. We have teamed up with Adesto Technologies and use their new Echo XIP memory. As mentioned before, it's a 4 MB octal SPI flash. There is a high-performance 8-bit double data rate interface between the flash and the processor, and the interface runs at 131 MHz. You might think that execution performance will take a serious hit when executing from external flash, but that is not the case. Just to give some numbers to relate to, running from internal SRAM gives a core mark score of about 3000 when running at 600 MHz core clock. Running from the Echo XIP gives a core mark score of about 1700. This is still a very good number. The power consumption of the flash is also very low, typically only 20 milliamps. For a more in-depth presentation about the use of external flash on the i.MX RT family, we have recorded a separate YouTube video and you see the link here. We have an i.MX RT1052 Developers Kit. It's a flexible hardware platform together with documentation and guides, and of course high quality support from us. And this is to get you up and running quickly for prototyping and building proof of concepts with the i.MX RT1052 OEM board. The Developers Kit has a 4.3-inch LCD with capacitive touchscreen, and there are USB, Ethernet, memory card, Audi and UART interfaces, and access to all expansion pads on the SODIMM connector. So that was our quick presentation of the hardware.
Thank you, Anders, for your excellent overview about the hardware. Hello everyone, my name is Vladimir Marchenko. I'm Product Manager for MDK at Arm, and in the next part of this webinar, I will demonstrate you application development and debug for the i.MX RT1052 device family using Arm Microcontroller Development Kit, MDK. I'll first give a short overview, and then we'll use an RTX5 RTOS application to show key debug and trace features. We will do some power measurement and pin control for test automation. After that, me and Anders will answer your questions. I strongly recommend you to view the rest of the webinar in full screen mode, as I will often show the application code and configuration dialogues that have small elements and are best visible in full screen. Okay, now let's get started. Many of you already know that Arm offers own professional software development tools that ensure vendor-independent and up-to-date support for Arm-based processors. And our Keil MDK is such a tool for Cortex-M devices. It provides leading support for more than 4,000 device variants from various chip vendors, including the i.MX RT family from NXP. This tool fully equips developers with the components needed to create, build, and debug embedded applications. MDK is based on Microvision IDE and debugger that you will see in action in just a few minutes. It also includes Arm C++ compiler that is tailored for optimum code size and performance. During the webinar, you will see how we use software packs to provide device support, as well as software components that you can use as building blocks for your applications. We also offer MDK middleware that provides royalty-free and tightly coupled software components specifically designed for communication peripherals in microcontrollers, such as TCP/IP, USB connectivity, file system, and Arm Mbed support. Finally, Arm also offers a set of ULINK debug and trace adapters that guarantee the best development experience with MDK. Now a bit more on the software packs that we use in MDK. Here we follow Cortex-M software interface standard, CMSIS. It increases your productivity by providing unified API to access generic processor resources. It has, for example, CMSIS DSP for digital signal processing and CMSIS RTOS for managing real-time operating system. It also defines the API for common peripherals such as UART, SPI, I2C, and others. The debug access to the chip is also standardized over CMSIS Dev. With all that in place, you can quickly develop complex applications that are easily portable across Cortex devices. You will see how this works later during the demo, where I will use CMSIS RTOS. So we worked closely with our partners NXP and Embedded Artists to ensure proper support in MDK for the i.MX RT device family and corresponding development board. Now let's see how this works. After opening Microvision, we can go to the pack installer, and once the pack list is refreshed, we can look into NXP devices and find there the i.MX RT1052 device family. Here it is. On the right side, you can see the CMSIS specs that provide device-specific support, as well as generic software components. There is a device family pack for this chip that is created and maintained directly by NXP. You can also see that we have a BSP pack with the support for i.MX RT1052 Development Kit from embedded artists. This pack also includes examples covering different functionalities of the chip and the board. I have both packs already installed and can go to Examples tab, and here I just start with an RTOS Blinky application. So I press the copy button next to it, provide the destination path, OK, and just wait a few seconds to get the application started in new Microvision window. In this application, a user LED is turned on and off every 500 milliseconds, and this toggling is paused when user presses and holds an onboard button. The application is simple, but it provides complete framework to easily add more complex functionality. So it is implemented using CMSIS RTOS API on top of our RTX5 RTOS kernel. In the application, we have several threads, and in blinky.c file you can see we create one thread for button actions and another one for the LED controls, using corresponding CMSIS RTOS API function. Chip and board configuration, including clock and pin settings, is done using components from NXP MCUS SDK that you might be familiar with. Low-level peripheral drivers are also same as MCUS, ensuring the best support for the chip peripherals. With the Manage Real-Time Environment window, we can manage the software components used by this application. Items that are already part of the project are highlighted in green, and we can easily extend its functionality by adding additional drivers, CMSIS DSP library, middleware components, and so on. Now, as I can't really show you the LED blinking in this webinar, let me add a variable that indicates the LED status. So I define it here, and you can immediately see in action our dynamic syntax checking feature that highlights potential issues while editing the code. In my case, this is a missing semicolon, and the red cross disappears once I set it in place. This really helps to catch typos or small syntax-related issues on the fly and improve developers' productivity. Finally, I set the variable values when the GPIO is changed. Next, using options for target dialog, we can further configure our project. We can, for example, select device variant or specify the output, and in our case, let's remove browse information to speed up compilation time. In C++ tab, we can specify the optimization level and add other compiler flags. The details of all the settings are described in our documentation, so I won't spend much time here, and we keep the settings by default. But to work with i.MX RT devices, it's important to look into the Linker tab. The i.MX RT1052 chip is special in a way that it doesn't have built-in flash. This is typical for high-performance Cortex-A devices, but not that common for a Cortex-M device. Using linker configuration, we can select the scatter file that instructs the linker to put the image correctly into the target memory. For this board, it can be an on-chip RAM, external SDRAM, or external SPI flash. My example is quite simple, so I will load it directly into built-in RAM and execute it from there. Additionally, we need to provide corresponding debug initialization file that ensures that this is correctly done during the debug as well. Here it is. All necessary scripts are provided together with the application examples. Finally, in the Debug tab, we need to select the debug adapter that will be used to program and debug the project. In my case, I will use Arm ULINKplus debugger. So let me just give you a brief overview of this debug probe. ULINKplus supports serial wire and JTAG interface mode via a 10-pin Cortex-M debug connector that is common to find on most development boards. But note that on ULINKplus, this interface also has built-in 1 kV isolation, making it a perfect match for sensitive applications like motor control or where high voltage power is involved. It also has two special interfaces, one for power measurement and another one for I/O pin control. Later in this webinar, I will demonstrate you how to use them. The initial hardware setup to get started with the application is quite simple. First, we obviously need to power the board. For that, I am using USB power and configure the jumper J29 accordingly. The board has a 10-pin connector for JTAG SWD interface that I use to connect to ULINKplus. One special modification we need to do on the board is wire connection between TP15 and TP83. This is required to enable SWO trace and is caused by specifics of SVO pin routing on this chip. Finally, specific for this Blinky application, a connection of the GPIO to actual LED 7 on the carrier board is needed. This is done by connecting TP96 pin to J8. I have prepared this setup already on my desk, so let's just get back to our example project in the MDK. I click on Settings next to the ULINKplus debugger, and if connection to the ULINKplus works, its firmware version is displayed. And if the debug connection to the hardware is established, you also see the ID of the Arm Cortex components here. Okay, now I can build the project. It takes a few seconds and compiles without errors and warnings. Next, I start the debug session. The application gets loaded, and then I can do all the common debug actions. For example, set a breakpoint, and then run to it, stopped, then do single stepping through the code. And you can see the gray markings next to the code lines indicate the executable code where you can actually put a breakpoint. The code that has been optimized or compiled out is not marked in such way and is easy to see during the debug. Let me add my LED status variable to the watch window. Just right click on it and add to watch 1. Here it is. If we run the application, we can actually see how it changes at runtime. And if I press the user button, the value freezes as expected. Now let's look into some MDK features that are especially relevant for high-performance devices such as i.MX RT, where you would typically run an RTOS and multiple software stacks and libraries. MDK provides you with additional information about the running software components. For example, there is an RTX RTOS view where I can see the status of the real-time operating system in my application. We can see kernel information here, and also the running threads are listed, and you can see our button and the LED threads, their stack usage, priorities, status, and so on. And we provide such views for all our middleware components, and it is easy to define such views for custom components or just for your application code. So in that way, you can always access critical status information during debug. But it is also possible to get a dynamic view into the software component using another unique feature, the event recorder. It lists the events occurring in the program over time. Our RTX5 RTOS is well covered with such events. They are also annotated with hyperlinks, so if I click on such event, then corresponding documentation page gets open. When I stop the program, I can save the event log or configure a filter to show only the events that are particularly interesting for me. The events are grouped by components and have different categories: error, API call, and so on. For example, let's just leave the events about RTOS thread API calls and run the program. We see now only thread flag wait and thread flag set events, as well as thread delay events are listed here. And this is exactly what is being used by the application. So we can see here we wait for a flag, then call a delay, and then set a flag. Now the event recorder is a powerful debug feature that is implemented with a special software component that can be easily added to any project. It uses RAM for the event buffer and is actually configurable. But then the data is delivered to the IDE using debug connection without stressing any peripherals such as UART or USB. You can also define custom events, and then once triggered, they would appear in the event recorder list. The features that I have shown to you so far are independent on the debug adapter that you use. But next, let's look at the feature that is unique to our ULINKplus debugger, its capability to measure core clock frequency. Today, microcontrollers have a complex clock setup with PLL configuration, multiple prescalers, etc., so it is easy to make mistake. And this is especially true for this i.MX RT1052 device. But with ULINKplus and MDK, you can easily verify whether the processor core frequency is configured correctly. For that, just open the System Analyzer window, and here we get the dynamic view into our system, mapping various data over time. The core clock row shows the system frequency that is actually being measured using the reference clock on the ULINKplus. As you can see, in the case of this Blinky application, the core clock is constant and is 528 MHz, which is a lot for a Cortex-M device. But the chip can run even faster, up to 600 MHz in the overdrive mode. So really high performance that typically would require a Cortex-A device. MDK needs to know this core clock value to properly synchronize to the trace data. So let me stop the debug session and then in the options for target dialog, the debug tab, then settings, and finally the trace tab, I can specify the actual core clock value, 528. In addition, we need to enable the trace and uncheck and check again the auto detect to properly calculate the SWO clock frequency. Just to remind you, the i.MX RT1052 chip has a special SWO pin routing that requires simple wire patch on the board. Okay? And then I restart the debug session. And start the program. Now the System Analyzer also shows the trace exceptions, and if I zoom with the mouse wheel, we can see these are the cystics, and we can put a marker and measure the time interval in between. It is 1 millisecond, as actually would be expected for a 1 kHz cystic timer that we use by default in our RTOS. We can also get a bit more statistical view into the trace exceptions, showing us the counts, min-max durations, the last time seen, etc. So now when trace is running, we can also monitor variable changes, and for example add the LED status. Just make a right click on it and add to Logic Analyzer. Now you can see how it changes its value over time. And if I press the user button, the toggling pauses correctly as well. We can actually measure the interval between the changes, and we can see that it is done every 500 milliseconds. The change is also synchronized with the SV calls in trace that happen when our threads are switching. Now, before we jump to the next topic and do actual current measurement on this board, let me just summarize the MDK debug and trace features. MDK supports hot plugging to a running target for status monitoring. It allows live watch of the program execution with value displays. It supports code and data breakpoints and provides status and event views for software components and user annotations. In combination with ULINKplus adapter, you can see the actual core clock frequency and benefit from the built-in isolation for sensitive analog applications. When serial wire trace is enabled, you also get statistics of interrupt execution, data trace of up to 4 variables, and a system analyzer that shows program execution over time. Excellent, let's move on. Modern embedded systems are often required to be energy efficient, and the i.MX RT device family allows you to run high-performance applications at very low power levels. So let me show you how to use ULINKplus debug adapter and do shunt-based measurements of the power consumption on the i.MX RT1052 Development Kit. For the power measurement, ULINKplus has a special 3-pin power interface that just needs to be connected into power supply circuit of the target system. This port has built-in isolation for up to 1 kV voltage, allowing you to measure power also before the DC-DC converter. Optionally, you can connect an additional shunt board to this interface to set up the proper limit for the current measurement level. So let's have a look at the setup required for the i.MX RT1052 development board. We need to keep the connections for the debug and trace as done in previous part. And this board already has multiple jumpers for power measurement. You can measure the current at chip level only, on the OEM module, just the ADC, and so on. And I will use the J3 jumper that allows to measure power consumption for the whole board. It already has a built-in shunt resistor of 100 milliohm, so I don't need to connect my own shunt board. So I remove the jumper and connect my power pins to it. The middle pin goes to the system ground that I use from the JTAG connector. Next, we need to configure power consumption in our MicroVision project. The easiest way to do this is with a special debug initialization file. We can find its template in the MDK installation directory. Then go to Arm, ULINK, Templates, and view all the files. And here it is. I just copy its content directly into the debug ini file that we use for RAM programming. After saving the file, we get the configuration wizard view that simplifies the configuration. So here we need to enable the power consumption measurement and select the shunt value used. You see that the shunt value of 100 milliohm is not present here by default. So I just go and add it directly to the ini file. Okay, and then save the file. Then it appears in the drop-down menu and I select it. Next, I restart the debug session. We can look into the ULINKplus window to verify the setup. Yes, the power measurement is enabled and 100 milliohm is correctly set as shunt resistance. If needed, it is also possible to change the settings directly here in the window. Next, let's open the System Analyzer window and run the application. Now you can see that the System Analyzer displays the voltage and current from the target system. Using the button freeze, we can stop the data acquisition and then analyze the recording. The voltage is around 3.3 volts as expected, and the current level is fluctuating around 190 mA. I zoom in with the mouse wheel, and the right mouse click allows us to change the filter characteristics applied to the measurement data. Higher values will show details of the current peaks, while lower frequencies will reduce the noise. The button Auto Min Max adjusts the range to fit the visible signal. In the current profile, we see regular spikes, and you can see that these spikes are well synchronized with the SysTick interrupts in the trace data below, and that perfectly explains their presence in the current profile. The interval between these spikes is also 1 millisecond. But the next obvious question is, what are these regular increases in the current consumption visible here? And I can tell you that they aren't expected in my Blinky application. If we take a closer look at them, we can see that they occur regularly with the period of about 30 to 33 milliseconds, what corresponds to about 30 Hz. I was puzzled and just asked Anders from Embedded Artist if he has any ideas about such behavior. His suggestion was that this can be caused by the touch controller integrated in the LCD screen. So we analyzed the board schematics and figured out that it is possible to turn off the power on this touch controller using particular GPIO pin on the i.MX RT1052 processor. Let me just add the necessary code for that at the beginning of my application. Okay, I rebuild the application and restart the debug session. Now those annoying current increases are absent, and we can have a closer look at the current change when LED blinks. Just apply the most suitable filter, and we can see the difference is just about 1 mA, as would be expected from a simple LED. You have seen that ULINKplus allows you to analyze power consumption of your application. In summary, it provides the following features. The independent electrical isolation of the power interface allows connection to any supply voltage, even before a DC-DC converter. Shunt resistors configure the measurement range. And the high resolution and linear behavior allow you to identify even misconfigured I/O pull-up resistors. The power measurement is time synchronized with program events and interrupts, and you can therefore identify the parts of the applications that change the power profile. The configurable filter parameters optimize the visualization depending on your needs. Now let's move to the final part of my demo, I/O pin control. As the microcontrollers offered by chip vendors become more and more powerful, just look at the i.MX RT family, so embedded software for them becomes more and more complex and requires use of automated test stands for high and documented quality assurance in the development process. ULINKplus offers the ability to communicate with the target under test using digital and analog I/O signals. For that, it has a special 11-pin interface. 2 pins are reserved for ground and 3.3 volt signals, and other pins can act as digital or analog input-outputs. As we will see next, these pins can be controlled and monitored directly from the Microvision IDE during debug, but even more benefits can be achieved using the scripting option and fully automating the system verification. Our application note 307 describes in details how to use this feature with the scripts and command line interface. In my application, I have a very straightforward hardware setup for the I/O controls. We keep the JTAG connection as before, and I will use pin 0 as digital input to monitor the actual LED status. hence connecting it to TP96 pin on the carrier board. Now let's get back to our application. Here in the ULINKplus window, I can configure and monitor the pin status. So our pin 0 is already configured correctly, and if I connect the wire on the board, you'll see how its status is shown here. In the same manner, the analog pins can be used. You can type the target value for the output or observe the measured value on the input. It is 0 here, as I have really nothing connected to this pin in my setup. Now, remember the debug initialization file that we used to configure power measurement feature? This one. It also allows you to configure the I/O pins prior to the debug. Here. Moreover, here you can implement own functions that can be called to trigger certain signals. And in this template, we have already a few functions present, and also the script that creates some user buttons in the IDE to trigger them. So I can call a sweep step function, and you see how it changes the analog signal. You have seen that ULINKplus allows you to control the hardware under test, but the overall functionality goes far beyond. You can build continuous integration tests and start the debugger in batch mode. You can create and measure signals. The debug functions allow scripting, and Microvision offers a remote control interface that you can use from other test applications. We are right in the end, so let me summarize you the key items we've done today in this webinar. First, Anders has explained you the i.MX RT1052 Developers Kit, and you've seen how easy it is to get it up and running. Then, we've looked into an RTOS-based MDK project and have used powerful debug and trace features in MDK. Finally, using ULINKplus debug adapter, we were able to measure power consumption and actually optimized it by removing the disturbing external impacts. We also controlled I/O pins for the test automation. You can always find additional information and documentation on our website. That was it. Thank you very much for taking part in this webinar.